good morning, good afternoon. It is my pleasure to introduce our first ISQGD special session speaker, Andre Ginchu. The title of his talk is The Extended Hausdorff Dimension Spectrum of a Conformal Iterated Function System is Maximal.
Thank you so much, Rinal, and thank you everyone for being here so early on a Saturday morning, or so early if you're here in US. I'm in Menominee, Wisconsin, where my university is, an hour away from Minneapolis, 3 hours from Madison, couple hours from La Crosse, where my friend Tushar is. He's going to speak at some point later today, I think, or maybe tomorrow, but I was very happy to see his slides already and some connections with the things that I'm going to say. I plan to talk for about 20 minutes, no more than 25 minutes for sure, just to give the chance for any comments or any last minute remarks. I met Ronnie Pavlov in 2017 at the conference that he organized in Denver. It was one of the special sessions, and I asked a question there. He had some great ideas, found the answer to a question that I asked. And then he invited me to Denver in 2022, and we worked on some research that ended up in a paper with the same title as the title of today's talk. And we were happy that the paper was published in the Journal of Mathematical Analysis and Applications. And I'd be, of course, more than happy to share this with everyone who might be interested in the details for this talk. So the overview of this presentation, we're going to talk a little bit about shift spaces, which we can think of as spaces of infinite words, whether they're in two directions or in one direction, with letters from some finite alphabet or some infinite alphabet. A particular case of shift spaces is represented by the beta shifts, which turned out to play a very important role in the research that we did. We're going to look at the connections between shift spaces in general, beta shifts, and conformal iterated function systems. And when it comes to conformal iterated function systems, the main subject or the main object of study is the limit set. And then we're going to look at the Hausdorff dimension spectrum associated to a conformal iterated function system, and how we can generalize these ideas. Namely, we can look at conformal graph-directed Markov systems, which essentially means that we place some restrictions. And finally, we can look at shift-generated iterated constructions. It's good if one has in mind the numbers in the unit intervals, and one thinks of the decimal expansions, how up to a set of measure 0, almost every real number has a unique decimal expansion, and how that is formed using the alphabet 0 to 9. And again, some of the restrictions that we place, we can look at that example and see how those work. The main question that my advisor, Dan Moldin, when I was a graduate student at University of North Texas in Denton, the main question, the Texan conjecture was, if you have a number in the unit interval, can one find a subset of the positive integer, so that when we look at the collection of all the numbers that have continued fraction expansions with digits exclusively from A, we form a set whose Hausdorff dimension is precisely that number T. Equivalently, we can go kind of the other way around and say, if we have a subset of the positive integer and look at the collection of all the numbers in the unit interval whose continued fraction expansions have digits from A, can we find such a subset so that the Hausdorff dimension is T? For a while, this was an open question answered positively for t between 0 and 1/2 by Moldin and Urbanski, and later by Marquez and Bome for all the values between 0 and 1. It was my dissertation question, and it was answered while I was working on that, and so I changed the direction of my dissertation and generalized this result to some other settings. But a more general question that we can ask now is, what if instead of the standard continuous fractions, we look at more general settings like a conformal iterated function system over an infinite alphabet? Same idea, if we have a subset A, we look at the limit set generated by that subset A of the alphabet I. If we look at the t between 0 and the Hausdorff dimension of the whole system, can we find a subsystem that generates a limit set whose Hausdorff dimension is t? And if this is true for every t between 0 and the Hausdorff dimension of the whole system, then we say that the system has full spectrum. And by the Hausdorff dimension spectrum, we just have the collection of all these values t that are Hausdorff dimensions of limit sets generated by subsystems. So this was the general question asked for various continuous fractions expansions for various other systems. The answer can be yes for many systems related to continuous fractions. Every iterated function system has a subsystem that doesn't have full spectrum. So the answer could be yes and no, depending on the setting. But the new question that I was looking at, what happens if the alphabet is finite? Is there a proper way to ask a similar question? Because with the finite set, the standard subsystems, we have finitely many. If we have 10 letters in the alphabet, we can have at most, I guess, 2 to the power 10 subsystems. So it doesn't, a question like that automatically is not true. Even if we place some restrictions, if we look at some restrictions on pairs in the alphabet, it's still finitely many subsystems, even if we enlarge that question. So the new idea here is rather than looking at subsystem in a traditional way, to say, okay, what if instead of subsets as subsystem, we actually look at shift spaces over the finite alphabet? And in that case, we have a continuum of subshifts or of shift spaces. And this question makes sense now to be asked. Just a few words about shift spaces. I'm pretty sure most of us are familiar with this. A finite or a countable set, that's the alphabet. The elements in this alphabet are called letters. A word is just a finite sequence of letters. The number of letters forms the length of the word. And I guess one important aspect here is that for iterated function system, graph-directed Markov systems, or for shift-generated iterated constructions, we use the one-sided full A shift, with the main difference between the one-sided shift and the two-sided shift being that the shift map in one case is 1-to-1. In the other case, if we have a finite alphabet, is k to 1 if there are k letters in the alphabet. The shift map is the traditional map for the left shift, just pushes or gets rid of the first entry. So we see how this is k to 1 if there are k letters in the alphabet. And this is a critical definition. A shift space or a subshift over an alphabet is a subset which is closed in the product discrete topology and invariant with respect to the shift, or alternatively, depending on the book you're looking at, you just define a set of restrictions, a script F, usually the set of restrictions that you don't want to see in those words. The traditional setting for iterated function systems is when we place restrictions only on neighbors, and so we only say this letter can follow that letter, or this letter can be preceded by that letter. And in that case, we call a topological Markov chain, we call it irreducible if for any two letters, there's a path that connects them. And we call it finitely irreducible if there's a universal length for the paths that connects any two letters or edges in the alphabet. And one can see, I guess, easily how if we have a finite alphabet, the two notions are equivalent. So this is about shift spaces. The language is the collection of all the blocks that we can see in these infinite words. And the N language just takes all the words of length N that we observe in these infinite words. This is terminology that is commonly used in shift spaces to define the entropy for a shift when we have a finite alphabet, and so on. So the beta shift is a shift that relies on beta expansions, or the non-integer expansions. Tremendous amount of work done for this kind of expansions, going back to Perry and Erdos and many others, Rennie, most recently Nikita Sidorov work on this kind of expansions. And so for a real number beta that's greater than 1, the beta shift is defined over the alphabet 0, 1, all the way to the ceiling of beta minus 1. The reason that we put the ceiling of beta minus 1 here is when beta is an integer. For instance, if beta if beta is non-integer, it's the floor or the integer part. But if beta happens to be 2, then it's not 2. It only has the digits 0 and 1. And so it relies on the greedy expansion, which basically says, grab the very first digit that you can. Don't wait until there's essentially no room. Roughly speaking, the difference between greedy expansions and lazy expansions. And so I'm just keeping kind of an eye on the time as well here. I emailed Mrinal the slides, and they'll be available. I'll be happy to email everybody the paper that I wrote with Ronnie. And so we'll go a little bit faster through some of these details, but here the first paragraph above the beta shift, it explains how the greedy expansion is defined. And then the beta shift can be defined as basically the closure of the set of all the sequences defined above. So just for a definition of the beta shift, known things about the beta shift, the entropy is log of beta. So for instance, if you define some iterated function system of similarities with constant ratio, then automatically the Hausdorff dimension is a constant times log of beta. Moving on, the shift-generated iterated construction basically is a very similar idea with conformal iterated function systems, with two main distinctions. One is the fact that we can have more than just one set now. With standard iterated function systems, the maps would go from a set Y into another set Y. Here we allow several possible domains, finitely many though. And the other possibility in a shift-generated iterated construction is that not only that we can have restrictions, but we can have any restrictions. In other words, they're more general than the standard conformal graph-directed Markov system because we can put any restriction we want. So rather we can say one restrictions, if we have the alphabet from 0 to 9, we can say we don't want to see 1, 2, 5, 7. And that's a restriction that in the standard setting of a conformal graph-directed Markov system was not possible, I guess, or was not looked at. The coding map is defined in a standard way. Start with an infinite word, take the first letter, take the second, and then go ahead and form a sequence of decreasing sets whose diameters converge to 0. And so when you do the intersection, decreasing sequence of sets whose diameters converge to 0. When you look at the intersection, then you have a point, a singleton, and then when you take the collection of all these images, one forms the limit set. A few other conditions here that make a shift-generated construction conformal, and I won't go through all the details. I will just point out to the second one, the open set condition, which is significant that we don't allow overlaps, or when we allow overlaps, things are much more difficult. People study systems with overlaps, but in this paper, or I haven't studied this kind of systems. Some other extra conditions, and one that's quite important for us is a consequence actually of them, the bounded distortion property. And I want to point out here this capital K. In a sense, this is a measure of chaos, if you want, in the system. The closer this K is to 1, one can look, very roughly speaking, as a system that doesn't have much chaos. If K is 1, we actually have similarities, so there's barely any chaos from that perspective, unless you place some other restrictions on the words. And a conformal iterated function system is just a shift-generated construction induced by the full shift and just one possible domain. And a conformal graph-directed Markov system, it's a iterated construction induced by a topological Markov chain. A few examples before we state the main results here. The Cantor set is a go-to example quite often. We can see here that essentially in the standard sense, we do not have any subsystems, or any subsystem would be either empty or just consisting of 0 or of 2. So essentially the limit set would just consist of 1 point. But when we go to decimal expansions, actually, it starts to be pretty interesting because the limit set generated by the decimal expansion is the full unit interval. The second we throw out any digit, pick 7, for instance, you throw that out, you don't allow the digit 7 in any of the decimal expansions, the limit set drops to a set of Lebesgue measures 0, and actually let's see, the Hausdorff dimension is ln of 9 over ln of 10. So this is a very, very interesting situation. It happens with any iterated function system. Standard continued fractions have been studied extensively. The first 3 examples here are actually conformal iterated function systems. The last one, the nearest integer continued fractions, this is a system that I studied, and we published a paper in the Journal of Number Theory a while back. It was co-authored with Sarah Mende and Mario Ra, both very good friends and collaborators. And this, to me, is one of the most natural occurring conformal graph-directed Markov systems, because naturally for this system, the digit 2 cannot be followed by negative digits. The digit -2 cannot be followed by positive digits. Any other digits, except for -2 and 2, there are no restrictions. But for this, there are. And the best part about this system is that its limit set is a full Lebesgue measure. We can do a lot of things when more things when we don't have a limit set of full Lebesgue measure, but that's the beauty of this system, I guess. So before moving on, the question now can be phrased like this. The question that I was mentioning earlier: is there a better way to, or a proper way to ask a question? And that question is, given an iterated construction over a finite alphabet, is there always a subshift generating a limit set whose Hausdorff dimension is any number that we want between 0 and the dimension of the full system? So I'll say this again. If we choose any number between 0 and the Hausdorff dimension of the full system, is there a subshift that generates a limit set whose Hausdorff dimension is that number? And the answer turns out to be yes, whether it's just over an alphabet of 2 letters or of 9 letters, like in the standard decimal expansions. Again, the value of this question is actually for finite alphabets, because for infinite alphabets, we have more room to work there with this kind of questions. And right now, this is a technical lemma. It's critical in the next result that we look at, namely that for any conformal iterated function system, so we started with conformal iterated function system, basically the function that takes beta into the Hausdorff dimension of the limit set generated by the beta shift is a continuous function. As a consequence of this, we have that for any conformal iterated function system over a finite alphabet, the extended Hausdorff dimension spectrum. And so we call the extended Hausdorff dimension spectrum, rather than looking at the standard subsystems, which were subsets of the alphabets, the extended Hausdorff dimension spectrum is the collection of all the Hausdorff dimensions of limit sets generated by the subshifts. And the main result here is that the Hausdorff dimension spectrum, or the extended Hausdorff dimension spectrum, is 0 all the way to the Hausdorff dimension of the whole system. So this is for iterated function systems over finite alphabet. And then we manage. It's not a surprise. It shouldn't surprise too many people that this could be extended to conformal graph-directed Markov systems. And so if we have a conformal graph-directed Markov system over a finite alphabet defined by a topological Markov chain, also the restricted extended Hausdorff dimension spectrum is the full interval 0 to the Hausdorff dimension of the whole set. So again, it's not written in these last two theorems. It's not clearly stated, but all we needed were the beta shifts. So, which was very surprising for me. It's quite an interesting story. I wasn't looking much into the beta shifts until I was going to give a talk at the University of Manchester in 2015 or 2014. It was about iterated function systems, and with about 2 months before, they said, well, we don't have much of an interest here in iterated function system. Would you mind talking about beta shifts? And so at that point, I kind of had the option, or should I tell them I don't know much about beta shifts, or should I just go ahead and look at them and learn about them and see how we connect them? So turns out that the beta shifts have a tremendous application and role in this. Thank you everyone again for being up so early. Thank you, Marinal, for putting this together. This is it. Thank you again.
Thank you. Is there any question to the speaker?
Well, again, I wanna thank everyone, and Rinal, thank you for putting this together. This is a tremendous opportunity to connect with new colleagues and with old friends. So thank you very much again. This is truly fantastic. Thank you.
Thank you.